Hello, everyone. Today, we are going to solve a system of polynomial equations. We have two equations in the system. One, second order, the other is of the third order. 2 times 3 is 6, so we may have up to 6 pairs of solutions, including complex numbers. Let's take a look at the equations. First, both equations are symmetric, which means if we switch x with y, we got exactly the same equations. For such equations, it's usually a good idea by using a substitution u equals x plus y and v equals x times y. For example, if x equals a, y equals b is a solution, then x equals b, y equals a is also a pair of a solution. That means in either case, we have u equals a plus b, or b plus a, or v equals ab, or ba. In other words, two pairs of x and y correspond only one pair of u, v. Therefore, this substitution might simplify the equations. In particular, it might reduce the order of the equations. So, to emphasize the advantage of the approach, I will also discuss another cheating method as a comparison. Let's solve the problem. From the second equation, x cubed plus y cubed can be factored as x plus y times x squared minus xy plus y squared. In the second parenthesis, we have x squared plus y squared. And we know it equals 61 from the first equation. Then we can replace x squared plus y squared with 61. We have x plus y times 61 minus xy equals 91. Then we do the substitution. xy is u, and x plus y is u, and x times y is v. We have u times 61 minus v equals 91. Now, let's look at the first equation. X squared plus y squared can be rewritten as x plus y squared minus 2xy. Then the second equation becomes u squared minus 2v equals 61. Therefore, we establish a system of equations in u and v. U squared minus 2v equals 61. U times 61 minus v equals 91. From the first equation, we solve for v in terms of u. V equals u squared minus 61 divided by 2. Plug in the second equation, u times 61 minus v, which is replace the expression in u, equals 91. Times 2 on both sides and combine the like terms, we got a cubic equation in u cubed minus 183u plus 182 equals 0. Look at the three coefficients. 1, negative 183, and a positive 182. They sum up to 0, which means u equals 1 is a root. Then we can perform a long division. The cubic polynomial divided by u minus 1. We have a quotient, a quadratic polynomial, u squared plus u minus 182. The quadratic polynomial can be further factored as u minus 13 times u plus 14. Then we have 3 pairs of solutions for u and v. U equals 1, 13, negative 14, and plug in the expression for v in terms of u. We got v have negative 30 for 54 and 135 divided by 2. So we have 3 pairs of solutions for u and v, and we know each pair corresponds to 2 pairs of x and y. This is exactly what we expected. The first pair, uv, is 1, negative 30. So we have x plus 1. X plus y is 1, and x times y is negative 30. Then, from Vieta's formula, we know x, y are the roots of a quadratic equation t squared minus t minus 30 equals 0. The coefficient for the middle term t is the negative of x plus y, and the constant is the product of x and y, negative 30. This equation has 2 roots, 6 and negative 5. Then we have 2 pairs of x and y. X is 6, y is negative 5, or the other way around. Similarly, if u and v is the second pair, 13 of 54, then x, y are the roots of t squared minus 13t plus 54 equals 0. The third pair, negative 14, 135 divided by 2. Then x, y are the roots of a quadratic equation t squared plus 14t plus 135 divided by 2 equals 0. These 2 quadratic equations give us another 4 pairs of solutions for x and y. They are all complex numbers. You may ask, can we solve the system of equations directly? Well, it is possible in theory. From the first equation, we times y on both sides. We got x squared times y plus y cubed equals 61 times y. Now, this equation and the second equation, they both contain y cubed. We can eliminate the term by a subtraction. We have x cubed minus x squared y equals 91 minus 61y. So this equation only contains linear terms for y. So we solve for y in terms of x. We have y equals x cubed minus 91 divided by x squared minus 61. We plug it in the first equation. X squared plus y squared is replaced by the expression in x equals 61. So we clean it up. Square, expand the square, and multiply the denominator. We got a polynomial for x, which is 6-degree polynomial. That means we have 6 roots for x. The question is, can we solve it? Or more clearly, can we factor the polynomial? Well, in theory, yes, but in practice, I don't know. However, I do know the factoring of the polynomial. It is something like this. And then the solution follows. The question, how do I know the factors? Well, from the previous approach, we got 3 quadratic polynomials in T as for 3 quadratic. Let's go back. T squared minus T minus 30. And the second quadratic polynomial T squared minus 30 plus 54. And the third one is 2t squared plus 28t plus 135. And then we replace all t with x. This is exactly the factoring of the polynomial of 6 degrees. Why? Because they are all the roots for x. This must be true, but you can verify that. So here is the thing. My suggestion is that when you solve the problem, you solve it using the first approach in scratch paper. And when you present the result, you write it up like this in the second approach. You do it step by step. No. From the first equation, we got this, eliminating y cubed, and solve for y, substitution, clean up, and then you pretend you factor the polynomial by hand, manually, and get things done. This way, people would be very impressed. Wow, how did you do that? Well, that's all I have today. Thank you for watching.